Welcome to part 3 of Lab 1, how to plot numerical data. So we've seen how in the first lab to enter in some of our own data, but we haven't seen much in the way of having to plot our own data. So in this lab we're going to look at that, and of course we're going to look at plotting some of the CDC data. Take some of our newfound skills from the previous activity and take those forward. So we've seen how to plot bivariate data before. Let's go ahead and go back into our studio here real quick. And so we know the plot command. So for example, if we go plot and we say CDC, let's say weight, W-I-G-H-T, and by CDC $, and we'll go by height. And so if we say plot those two, we get the following scatter plot. Let's go ahead and make that a little bit easier to see here. I'm going to open that up just a little bit. We can actually do the zoom command here, and that'll actually make the picture go full screen. And we see, what we've looked at before in terms of scatter plot. On the x-axis, we've got the weights, and the y-axis, we've got the heights. Okay, so we've looked at how to plot numerical bivariate data, but we haven't really talked yet about how to plot a vector or univariate data. And as it turns out, there are two very popular plots for those types of data that hopefully you've done some reading on at this point, and that would be the histogram and the box and whisker plot, or the box plot. Both of them have their uses. They're both very useful plots for looking at single variable data. One of the things that the histogram gives us that's very important is the shape of the distribution. The box plot is good for comparing multiple populations to each other on the same plot. That's a good single variable. So if you want to look at multiple single variables and compare them to each other, box plots are really good at that. Okay, so let's start off with the box plot, and let's go ahead and look at a box plot of the heights. Okay, so to do that, we'll type in box plot, and then if we wanted to do it on all the heights, we would go CDC $HEIGHT, and bada bing bada boom, we get a box plot. It's so nice how quick that happens. Later not in this particular video, but later on I will be doing a video that's just on how to gussy these up a little bit and how to make the box a different color if you'd like, but more importantly how to label your box plots, and I'll show you how to do that. Okay, so let's take a look at a summary here. Go ahead and do summary of CDC heights, and just talk a little bit about what the box plot just gave us. Okay, so the thing to notice here is that the minimum number 48, that corresponds to this dot down here. In other words, that's the smallest point. That's the minimum in our data set. This value right here, 64, that is the first quantile, or Q1, which means that 25% of the data fall below that number. Notice that 64 is this edge of the box right here. The median at 67. 67 is this dark line in the middle of the box right here. That falls right there. Q3, which is our third quartile, that's at 70, which goes right here. So height of 70 inches was the third quartile. And then the maximum was 93 inches. Ooh, tall person. And that's this point right up here. NBA player probably, huh? Now, what are the rest of the features of the box plot about? Well, these values right here, these hinges or whiskers, end of the whiskers right here, those values are exactly 1.5 times the interquartile range above Q3 and below Q1. In other words, we know that this distance right here from Q1 to Q3 is the interquartile range. So we took 1.5 times that number, and they made that a measuring stick and measured from here to here. And so this distance from here to here is 1.5 times the interquartile range in both sides of it. All right. And then any value that falls outside of that data point, the last data point that falls within those intervals, is considered to be a suspected outlier. And so we change the plot on those and make them into dots, showing that those are values that we suspect are different than the majority of the data set that we have produced. Okay. All right, cool. So that's a little bit of good on the box and whisker plot. Let's take a minute real quick and talk about model formulas, because one of the things that we'd like to do is do comparative box plots. In other words, we'd like to be able to plot more than one box plot at a time on a coordinate system. And as we'll see that there are multiple ways of doing that, but one of the nice ways of doing that, and it's a great place to introduce it, is what's referred to as a model formula. And as it turns out, we've had experience with this style of notation in our algebra classes. So if we come back over here to the whiteboard real quick and I get a fresh whiteboard, if you recall back in algebra, we had the y equals f of x notation. My pen's a little thick here. Let me turn my pen down just a smidge. Okay. So here, let me clean that up to try that one more time so it's not so ugly. So if you recall back in algebra, you got y equals f of x, or the function notation. And basically what that says, it says that your response, if we think about this in terms of our current work in statistics, your response is equal to some function of the predictor variable. And so we would call this over here the predictor. And so there's some input. We put in some input value x, and when we put that in, the resulting output value, that's going to be this value over here, the y. So back in the language of algebra, this was called the input, and this value over here, the y value, we called that the output. Okay, well, in statistics, very similar sort of idea, but what we have now is we have a predictor. You input something into the predictor and it gives you back some sort of a response. All right. So, for example, here in R, we can build what's referred to as a model formula, where we would say, well, I think that the height, perhaps, can be modeled on gender. In other words, if I know what the gender is, there's going to be some sort of predictability to what the height is, right? In other words, we know that, most of us know that males tend to be taller than females, right? And so the predictor, the gender here, if we give the gender as a predictor, it'll tell us something about the differences in the heights. So that's the basic idea behind what's referred to in R as or in many times in statistics as a model formula. And so we're going to use those to help us do side-by-side comparative box plots. So let's go back over to RStudio now. And let's go ahead and do that. All right. So we're going to go ahead and build a box plot here, where we go box plot. Better click on there we go. We'll go box plot, and we're going to give it two variables. We're going to say CDC height, H-E-I-G-H-T, and now you need the tilde. That's our model formula builder. The tilde is up above your tab. You see it's the second function for your tick mark. Okay, so if you give that character, that is the thing that says this is being predicted by this, and this is being predicted by this, is the height is being predicted by whatever your gender is going to be. Okay, so if we do that, notice we get side-by-side comparative box plots, where the box plot on the left represents just the male heights, and the box plot on the right gives you back the female heights. And as we said, we've predicted that the distribution of heights of the males should be in such that most males are taller than the females. And as a matter of fact, that's borne out by our side-by-side comparative box plots. Remember, the dark line in the middle is the median, which is one of our measurements of center, one of our measurements of average. And so we see that the box plot for the males is shifted up higher than it is for the females, thereby inferring to us that heights of males are larger or taller than that for females. Okay, so another thing that we can do in RStudio is we can actually build new variables from old variables. In other words, we can take a formula and generate a new variable from an old variable. So in the lab, the way they talk to us about this is, let's go ahead and calculate the BMI for everybody, which is the body mass index, which many times is considered to be a much better predictor of overall health than weight would be. So to build BMI, we're going to go BMI equals, we're going to create a new vector here, and that vector, that variable, is going to be the weight divided by the height times 703. That's just the formula for doing that. So we're going to go for the numerator, the CDC weight, and we're going to divide that by CDC height, and then we need to multiply that times 703, which is the fudge factor to make it work so that these numbers come out in the right units. Okay, so oh, I might bad. I'm sorry, it's the height squared. Almost made a a dreaded mistake there. Okay, so let's back up here for a minute. Put the right formula in there, and you'll get back out the right result. So let me go ahead and trap CDC weight divided by CDC height, and then caret 2, that means to square it, and then close off the parenthesis. Okay, yeah, much cleaner version of the formula. Sorry about that. So take a second and edit that if you need to. If you'd already hit an enter, just remember you always hit an up arrow and it'll replay the last thing that you did. So hit an enter, and now if you come over here under values, it's not a data frame, so it's a vector. It shows us that it has one variable with 2,000 entries in it. Okay, so then gives us some samples of them right here. So those are the examples of BMIs. Okay, so let's go ahead and do a box plot of the BMI to start off with. They don't ask us to do this in the lab, but let's just do the box plot straight up for just a second. So let's go box plot BMI and hit an enter, and then that's the box plot of our BMIs. And what we see is that most of the folks have BMIs that are, 50% of the BMIs fall inside of the box right here. And so those range to, less than 30 and greater than 20. If I want to know exactly what those numbers are, of course, I can go in and go summary BMI, and it tells me that it looks like that 50% of our body mass indexes are between 22.71 and 28.89. So that's being the box in between there. Okay, and then there's some rather large BMIs up here at 73, and then rather small ones down here at 12.4. Okay, so we can do a BMI by what was the predicted general health. If you remember that we had one of our variables here, let me go ahead and again give you the top 6 rows of CDC. And one of the variables we were given was general health and what people said their general health was. So let's take a look and see if there's a relationship, doing side-by-side comparative box plots, between the BMI and what people said their general health was. So to do that, we go box plot, parentheses, BMI, and then again we're going to put in for model formula. See, we're saying, is there a relationship here? Show me the relationship between the body mass index and what people predicted their general health was. So we go CDC and then gen health. Okay, hit an enter, and voila, we get, look, a side-by-side comparative box plot for excellent, very good, good, fair, and poor. Now notice the very good didn't show up because it's hard to see in this here. So if you click on zoom, it'll expand it out to the full size for us, and we'll be able to see all the labels. And what we see is there appears to be a trend in the BMI as we go from excellent to poor, is that the BMI seems to be increasing as people's health seems to be getting worse, which is, one of the things they say is that BMI is a reasonable predictor of a person's health. The larger your BMI is, the less likely you are to be healthy. Okay, so pretty nice graph, very, very good at giving us that information. So one of the things about statistics is that many times the information comes from visuals and from graphics. Okay, it's a nice way of seeing things. I think, again, to remember one more time about a box and whisker plot is that 50% of the values reside within each of the boxes too. That's an important thing to keep in mind. Okay, let's switch gears here for a minute and let's go talk about histograms. So histograms, unlike box and whisker plots, are not very good at comparing multiple populations. It's difficult to plot multiple histograms on top of each other, where box and whisker plots, it's easy to put multiple of them on the same graph and then compare them to each other. But what histograms are very good at, and what box plots are not very good at, are showing the shape of a distribution. You really don't want to take a look at the shape using a box and whisker plot. It's a very poor predictor of what the shape of your distribution is. It mirrors the shape of the histogram, but you can't infer from the box and whisker plot back to the histogram. Now, another quick comment on shape before we go any further is that shape is for numerical data. When we're talking about the shape of a distribution, we're not going to be referring to that at all when we're talking about categorical or qualitative data. Only for numerical or quantitative data do we consider talking about the shape of the distribution. Okay, all right, so let's go ahead and take a look at the histogram. Let's start off with a histogram of the age. So to get a histogram is very simple. You just type in hist and then go CDC age. And that is the histogram of the age. And what we see is across the x-axis are the ages, and on the vertical axis is the frequencies, or how often each of those occur. And what a histogram basically does is it takes the data and it breaks it up into what are referred to as bins. And the bins are these intervals along the x-axis. And then what you do is you count how many of the data points fall into any one of the individual bins, and the height of the bar gives you the frequency of the number of data points that fell within that bin. And one of the things that you can see here is the shape of this distribution is skewed to the right. If you think about our work in the last module, we already started talking about the shape, as whether we were skewed right, skewed left, or unimodal when we were talking about predictors like the mean or the standard, the mean or the median. Okay, so this distribution appears as we would think. With ages, it tends to be skewed to the right. There's very few really old people, and then there's kind of a clump of younger people in the middle. So we would say that this distribution is skewed to the right. And referring back to our measurements of center, when you have a skewed distribution, it's not a good idea to use the mean for your measurement of center. You want the more robust statistic, which in this case would be the median. The reason for that is that the mean loves extremes. It gets dragged out towards those large values and gets shifted away from the center, where the median is more robust and it's more resistant to that. And it still just splits the data in half. 50% of the data falls below the median and 50% of the data falls above the median. Okay? All right, let's go ahead and take a look at our BMI. Let's see what the histogram of BMI looks like. So if you go hist BMI, notice it's not part of a data frame. It's a single variable. It already has been ripped out. Here, come back up here and take a look at our data, and you see that it says values. This is a single variable with 20,000 entries already built into it. Unlike up here, CDC, that's a data frame which has 9 variables in it. Okay, and so back here, whenever I wanted to do CDC of the age, I had to tell it which variable I wanted. Okay, so drum roll please, and there is a histogram of our BMIs. And what we see is that there's some pretty extreme outliers in here. We saw that actually in our box and whisker plot, and so we may want to change or refine the size of the bins, kind of make them so they're a little bit smaller. And so one way you can do that is with the breaks command. So if you come in here, hit an up arrow to replay the hist, and then put in breaks, and then put equals to 50, that's a good way to increase them. What that does is, you can think about it, what I did is I increased the number of bars so that I have 50 bars there. That's an easy way of thinking about what breaks did. It says break it up into 50 bars for me. Let's go ahead and look at that in full size and zoom it. And what we see is that BMIs, again, have got a long tail to go out to the people who have this extremely large BMI. So again, this data set is going to be skewed to the right. It's got some pretty extreme outliers in it. And again, the best measurement of center would not be the mean here. The best measurement of center would be the median. Okay, so even though they didn't ask us to do it, let's take a look at one that should be roughly symmetric. And so we should go histogram CDC heights. Let's go take a look at the heights. I'm curious to see what the histogram of the heights looks like. Now let's go ahead and do that with more breaks. Let's see if breaks equals to 50 works here. May have to adjust that number. Yeah, looks pretty good. Okay, there we go. So the histogram of the heights, what we see here is it doesn't look like that there's a tail on either end, that it's clumped mostly around the center. So this distribution could be inferred to be unimodal or roughly symmetric. And in this case, the mean would be your best measurement of center. You would not use the median here, okay? So when you're working with a distribution that has roughly a bell shape to it, then the mean is your best measurement of center. On the other hand, when you're working with distributions that look like this, that are skewed to the right or skewed to the left, then the median is your best measurement of center. And then correspondingly, when you're using the mean for your measurement of center, as we would do on this histogram, we would use the standard deviation as our measurement of variability. If we were using the median as our measurement of center, then we would use the interquartile range as our measurement of variability, or the 5-number summary. Okay, so now it's time to go do the on your own. So what we're going to do is open up a new R Markdown file. So go up to your little plus tab up there and say, I want to make a new Markdown file. I'm going to call this assignment 2. And we're going to get a new R Markdown file. And so the first thing we're going to want to do is come in here and get rid of all of this sample stuff, the stuff that we did in our test file. So that's going to be typical of what we do when we work in an R Markdown file. The very first thing we do is get rid of all of that boilerplate stuff there that was trying to give us a little bit of help. Now, another thing I would strongly recommend you do when you start working in an R Markdown file is to go open up the R Markdown quick reference and have that open over here in your lower pane. That helps you remember some of the syntax of things, like, what does the hash marks mean? How do I put in an R chunk of code? How do I do inline coding, etc.? Okay, really useful little cheat sheet off to the side here. I got to admit, I use it all the time. So I've been doing this for a while, and I still open that thing up and have it over there to remind myself what to do. Okay. All right. So we're going to go ahead and put in Lab 1 as the beginning of assignment 2. So I'm going to come in and put in 4. I'm going to click back onto the lab here. There we go. I'm going to go put in 4 of those hash marks, and I'm going to type in Lab 1. Lab 1. There we go. Okay. All right. So because the data set that we've used here, the CDC data set, doesn't just like live in R, we need to actually put it into our lab here, into our assignment, so that R knows to go open that up if we execute this later on and it's not already sitting over here just waiting for us. So to do that, we're going to go ahead and make an R chunk. So we're going to insert an R chunk. Whenever you insert an R chunk, it automatically puts the cursor over here next to the R. You got to move it down so it's between the tick marks, okay? And then scroll back up to the very beginning of the lab and highlight that very first input line that we did way back in the beginning of this lab, the source command, and go ahead and put that in right here. Okay, so we paste that in, then that will make sure that that data gets into here every time we need it. Now, if you haven't done it yet, please go ahead and save this file. You should save it. I've actually been working with this a bit, so I've already saved it, and save it and call it assignment 2. And if you go into file, you'll see some files down there. I've had to actually restart this video, made some mistakes, and so I had to go fix some things, and so it's a little, hopefully not too inconsistent. My inconsistencies hopefully don't show up here. Okay, so once we've done that, now we've got the ability to open that. Let's go down and go grab what they want for us to do here. Let's go grab question 1. But before we do that, we'll go ahead and put in, say, 5 hash marks, and we'll put in on your own. All right, let's go get number 1 here. And number 1, it says make a scatter plot of the weight by the height. So we'll copy that out of the lab actually and just come in here and paste that, okay? So it says make a scatter plot of weight versus BMI, not height, excuse me, but BMI, and describe the relationship between these two variables. All right, so we're gonna have to open another R chunk here. And again, we have to, as with the source, we're not sure whether or not BMI is going to be sitting over there defined for us. So I'm just going to come back up here into the earlier part of the lab, and I'm just going to go ahead and highlight that line out of the lab that defined BMI for us. So we'll go ahead and paste that in. Now notice they're using the left assign. If you don't like that, you can replace it with an equals, or you can just leave it alone. It'll totally understand it, okay? So that's the command to actually create BMI. And they want us to make a scatter plot. Remember, a scatter plot is the plot command. So we're going to plot the weight versus BMI. So that's weight, and then you're going to do that comma, and then BMI. All right, now I'd like to execute the R code that I have done so far. So let's go ahead and save this, and let's go ahead and knit what we've done to date. Okay, so let's go ahead and say knit HTML. Let's see if what we've got done so far works. Oh, we've got an error here. Let's go ahead and see what the error is. Well, that was a duh. It was a very simple one. I forgot to put the CDC in here. I tell you. Now, let's try that again. That was good that I actually did that. I would hate to do that later on. Okay, so let's go ahead and try one more time. grind, 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 and lo and behold, there we go. It actually made the document for us. Okay, that's nice. If you read in there, if you ever have any trouble with any of your R code, don't be shy about just cutting and pasting that, sending it into a discussion for me where we can all look at it. And if you see it, the fix before I do, please help people out. Okay. All right, so looking good. Looks like we got it per document going pretty well here. One thing that's nice I want to point out to you is you can actually execute your R chunks without having to knit the entire document. If I go in here and just get inside of this current R chunk that I'm in between lines 15 and 18, and then go over here to chunks, you'll see where it says run current chunk. So if I click on that, it'll just act as if I was working in the console, paste those commands in the console, and then come over here just as we were working in the console and not on an RMD, which is really nice because that's the way you can check and kind of debug your R chunks without having to re-execute the code every time. Well, what do we see in this graph? Well, we see the BMI increases as the weight increases, as we should suspect, right? Okay, cool. Let's go ahead and take a look at part 2 of this. And part 2 of this particular problem, they say, all right, what we want you to do, I'm going to put a space here just to make it visually a little easier for me to see what's going on. So it says on your own, it says, tell me whether or not there is a difference in the way of weights of men versus women using side-by-side comparative box plots. Okay, so whoops, that wasn't what I wanted. I wanted you. You obviously didn't copy for me. There we go. Okay, so come back over here. All right, so using numerical summaries and side-by-side box plots describe if men tend to view their weight differently than women. Okay, so let's go ahead and insert a new chunk here. Okay, and so what we're going to have to do is create a box plot of weight by gender. So we can do that fairly easily using a model formula. So if we go box plot and we go CDC weight, I'd like the weight to be conditioned. Let me get that $sign in the right spot there. I'd like that to be conditioned by what? CDC gender, right? So in other words, create the box plots based upon the predictor would be the genders. So that's going to give me 2 side-by-side box plots of weight by gender. So let's go ahead and just execute that chunk, make sure that that's working. Sure enough, there we go. We got our side-by-side comparative box plots. And what do we see? We see that the weight of the men is larger than the weight of the women. Well, again, it's kind of a duh, but that's all right. This is more of an exercise in getting you to see how you can get data to tell you stories that maybe you already knew the answers of before. So that's nice because it kind of makes it so that your intuition is well played out by the analysis of the data. Okay. Now they also asked us to take a look at the summaries. They want to know the summaries of those 2 data. So we're going to need to go in and create a couple of more data frames here. So we're going to go ahead and make the male data and the female data. Of course, we're not going to assume that the male data is in here just as we have earlier. So we're going to go ahead and create that. So we're going to go mdata is equal to, and we'll go subset, just as we did before, CDC, comma, CDC $gender equals males. Okay, so what that's going to do is that's going to create the male data set. So we can actually go ahead and run that chunk again. No big deal. Doesn't even look any different because it just created the same data set that's already up there. So let's put in the F data, which is the female data, equals subset CDC, comma, CDC $gender, in this case, is equal to female. Again, one more reminder, if it is a categorical variable, then you need to put it in quotations. If it is a numerical variable, then don't put it in quotations, okay? When you're working with this, with the logic that is, all right? All right, cool. So that creates those 2 for us. And so now what we can do is we can get the summary data for each of those. So we can say, okay, give me a summary of the male data for their weights. So that's a summary of the male weight data. And then let's do this one more time. Let's get a summary of the female data weights. So this is looking at just a single variable. We're looking at just the variable with the weights out of the men's data frame and the variable for the weights out of the female's data frame. Okay, and so if I run that current chunk, I get our box and whisker plots, and I get the summaries for the men's data and the women's data. So we see that the men, on average, if we use the mean here, is about 189 pounds, and for the women it's about 151 pounds. Looks as if we've got some suspected outliers, some very large numbers reported in here, so it may be that these data are skewed, and that's kind of, we should do a histogram for each one, but I can kind of see we've only got a lot of skew going on in both of these on the right side. So the better measurement of center in both of these are probably going to be the median. You can see that in this case the means are larger in both cases than the medians. That's actually compelling evidence to say that, hey, you know, I think there's a possibility to have a skewed right data set. Okay. All right. So determine if men tend to view their weight differently than women. So we're going to go ahead and answer here is men's weight tends to, or men's weight tend to be larger than women's. And again, like I said, not exactly earth-shattering information, but that's okay. We're getting the idea. That's the main thing, how to use this stuff. All right, now the last one is a challenging problem. This is the third one, and that is what they want us to do is they say, get creative. Okay, yeah, whenever I hear that, it's like, okay, yeah, you want to beat up on me now, don't you? Okay, so number 3 here says, now it's time to get creative. Find the mean and standard deviation of the female weight variable and determine what proportion of the weights are within one standard deviation of the mean. Okay, so let's go ahead and build another R chunk. Insert chunk, okay. And we're going to have to go create a couple of things here. We need to know what the mean of the female data is, and then the standard deviation of the female data. And then we're going to have to go ahead and use some logic to create an interval of that data, okay? So let's take a look at how we can do this. So we're going to go in and make a few values first. We're going to store into X bar the mean of the F data, oops, female data weight. Remember, you can pull out any one of the individual summary numbers using its corresponding command, okay? And then we'll say the standard deviation, we'll call that STD for standard deviation, and that's going to be equal to SD. Remember, that's the command to get the standard deviation for the female data weight. Now what they're looking for is they want to know what proportion of the weights fall within one standard deviation either side of the mean. Okay, so let me just for a second, before we go any further with this, let's go draw a picture that kind of explain to elucidate what the heck they're talking about here. Okay, so let's get a fresh whiteboard. There we go. One too many. There we are. There. Okay, cool. All right, so if we took and we drew a number line here, and we marked on that number line what the mean of the female's data weight is. We'll call that X bar because that's the variable that we're going to name it, okay? And I say I mark that there, and what I want to do is I want to take a measuring stick, and my measuring stick is going to be basically the length of a standard deviation. So I'm going to go out one standard deviation this way, so this is an SD right here, okay? And then I'm going to go out one standard deviation this way, and that'll be an SD in that direction. And what I'm curious at is that if I notice that I mark these places on my actual axes here, this is going to be X bar plus one standard deviation, okay? And then down here, this is going to be X bar minus one standard deviation. And so what I'm curious about, the question is it wants to know is what proportion of the data falls in this interval from here to here. Okay, so how many of them divided by the total amount fall inside of that interval? So that's what we're trying to actually do. So let's go back into RStudio for just a moment here, and let's go execute this chunk. So we have some numbers to look at here. Okay, so we're going to actually go ahead. I'm going to go down into the console and echo those just for a moment. When we do the when we build it, it'll do this on its own. But for the moment, let's just go ahead and do this. So let's go back and take those two numbers. They're basically 152 and 34. And so if I come back to my drawing for a minute. So the mean here was 152. So this value right here, change colors here one more time. This is 152 plus 34. And this is 152 minus 34. In other words, that's what those numbers are. And so those endpoints right here, what I'm going to do is find out what numbers fall in that interval. And whatever numbers fall in those interval, I'll count how many of them are in there, and I'll be able to tell you actually what the proportion is going to be. Okay? All right, so let's go back into RStudio and let's do that. Here we go. Back into RStudio again. Alrighty then. So how do we actually do that? Well, our first thing we've got to do is go create that interval. So to create that interval, we're going to call that interval 1SD for one standard deviation. And the way you're going to do that is going to again use the subset command. And we need to go into what? Well, we're collecting data out of the female data. And what we want to do is we want to take the female data weight, and we want to gather those weights so that they are above that lower number. So that's greater than, well, what do? We called it x bar minus SD, or STD, excuse me. And we want to also take the female data weight, and what we want for there is we want that also to be what? Less than, so we're trying to trap it between those two, x bar plus STD. Okay. All right, let's go execute this R chunk just to see what happens at this point. Okay, so we'll run current chunk, and notice we get a new variable called one. Let's see, where'd you go? Should be up here. Bmi. There we are. There's one SD, and what we see is that there's 7,820 observations on our 9 variables. So what we can do is we can come over here now. Let me scroll up here. Is we can come in and ask for, take the dimension of our 1SD, and we can divide that by the dimension of the F data. And what that's going to give us back is, well, both of them have 9 variables. So we're going to actually get 2 numbers. We're going to get the ratio of the F data. Let's go over here where the F data is. That's 10,431 divided into the 7,820, and then 9 divided by 9, so that's going to give us back a 1. Okay, so let's just run this R chunk that we're in right now just to see what it's going to give us. So run the current chunk, and sure enough, what do we see? We get back basically 75% of the data falls within one standard deviation, and this one right here, that was 9 divided by 9. So you need to ignore that because that's not the number we really need. Okay, and so coming down here, we're going to say it appears that about 75% of the data fall within one standard deviation of the mean. Okay, cool. That was a long, arduous path. Hopefully you got something out of that. Go ahead and save that real quick, and go ahead and knit it. Let's just make sure it's going to work and not blow up on us. This is a a very complete lab, and that it contains a lot of information, and we're not expecting, myself, and I don't think the authors either, expecting you to understand everything that you did here in one sitting. So we're going to go over this stuff over and over and over again until it starts to become second nature. So if you're feeling a little overwhelmed at this point, that is okay. That's pretty common at this point. In fact, I would be surprised if you were not feeling overwhelmed. All right. So hang tough, and we will get there. Okay. It will start to make sense. So I got a little bit of a mistake here. I want to put a space in there. Let's go ahead and do that just to fix that. Should always put a blank in there just to kind of get things away from each other. Okay, so I'm going to stop this lab here, and I will see you all back soon.